Welcome to Math 383 Complex Analysis. What we're going to do today is we're going to finish the analysis of the proof of the Riemann mapping theorem. I want to adjust things a little bit from previous years. And this is one of the advantages of having the videos from the other years, as well as having a pretty good book, is that I don't have to keep doing the same thing each and every year. I have the option of exploring things a little bit differently and trying to emphasize different items. If you are having issues, by all means, please email me. If I'm in my office, it's office hours, unless I'm in my office stuck in a Zoom meeting, in which case then things have changed. So I'll quickly review Mantel's theorem and some of the analysis results, and I'll sketch the proof of the Riemann mapping theorem. And I want to give a lot of examples of items in the proof, trying to emphasize the general item we always discuss. What is the difference between real and complex? Why are they so different? So what are the inputs that give us such wildly different results in complex analysis from real analysis? All right, I will try to fill in most of the theoretical details. It's very easy to get one or two of them wrong. I apologize for mixing up where the radii should be for the proof of the first part of Mantel last time. This is why it's always nice you can just go back to the books, go back to a lecture where I did not screw it up. All right, so just a quick review of the terminology that we're supposed to have. A family is normal if every sequence in F has a subsequence that converges uniformly on every compact set. Given that group theory is taught in this class beforehand, it was good that Professor Lipp erased everything because she could have a different definition of normal on the board right now. This is our definition of normal. So every sequence has a subsequence that converges uniformly on every compact set. The limit need not be in the family. Why do we like working on compact sets? I mean, we're always talking about mapping from an open set, so why do I want to do things on compact sets? Yes?
Compact sets go to compact sets.
Compact sets go to compact sets?
Open sets means not.
At least if you're looking at a real mapping. Now in complex, the image of an open set is open. So what good properties does a compact set have? Bounded. We could have a bounded open set. Sequences accumulate, and they accumulate to something in the space. So in terms of convergence issues, it's much better for working with a compact set. Okay, a family is uniformly bounded on compact sets of omega if for every compact set there exists some b such that the absolute value of F is at most b. By now you should know I absolutely hate this notation. What do I want to replace? Yeah, I want this to be bk. Right. I want to remind myself that the constant depends on the compact set K. And then the last is a family is equicontinuous on a compact set K if for every epsilon there is a delta such that whenever Z and W are in K, then if Z and W are close, then the functions are close. And I can do this uniformly. My delta is not going to depend on my points. If I have more than one compact set under consideration, then of course delta could depend on that compact set. But I'm talking about right now equicontinuous on a compact set. So I fixed the compact set K. If you want, you can write delta depending on K, but there's just one K under here. In the previous one, we're talking about on compact sets of omega. So we're thinking of an exhaustion where we take a sequence of compact sets that are expanding out and filling up to our open set. So if you want, think of it as all points that are at least, say 1 over n from the boundary. And as n goes to infinity, the compact sets will be expanding out. All right, so here's Mantel's theorem. We did the first part, did not do the second part, but that was, I think, in the lecture I had you watch. Suppose F is a family of holomorphic functions on omega that is uniformly bounded on compact subsets of omega. Then we have two items. The first is F is equicontinuous on every compact set of omega, and the second is F is a normal family. And what was the key ingredient we used that was different in complex analysis that we did not have at our disposal for real analysis? So we were trying to prove this equicontinuity. Yes. And I guess if I just say you are correct without saying out loud what you said, that would be considered cheating. So I will say, yes, we use Cauchy's theorem. I'm trying to be honest here. And so that is a result that we do not have in the real case. We have an integral representation. Now you could ask, maybe there are better analogs for real analysis than just a standard differentiable analytic function. Maybe I want a real function that is given by some kind of integral. Well, let's see, if you're in the real line, an integral over the boundary is just what? Its value at the two endpoints. So if you try to think about what would the analog of some kind of integral representation be, that seems like it's going to be a very restrictive condition on the functions you'll be looking at. Okay. So there is a result that you should have looked at in the video. If omega is a connected open subset of C, and we have a sequence of injective holomorphic functions that converges uniformly on every compact set, then F is either injective or constant. Can somebody give me an example of a sequence of functions that satisfies all these conditions and converges to a constant? So you have to tell me from what to what, and Fn of Z equals what. So I want an example. And I want the limit of Fn of Z is constant. So what do you want that constant to be? 0, right? Might as well make it 0. If it's not 0, just subtract 5 or whatever that number is from everything. So omega is a connected open subset of C. What connected open subset of C would you like to look at? Yep, the unit disk. Good choice. All right, so it's going to be mapped from D. Where do you want it to map to? Yeah, let's say D to D. Okay. So I want a sequence of functions that map D to D, and their limit is 0. And each one of them is injective. Any thoughts? 1 over n times Z, or Z divided by n. Either way works. Right? So here's a really nice, simple example. For any finite choice of n, it's clearly going to be injective. But the limit is going to not be injective, but it's going to be a constant function. So whenever you see a statement like this, then F is either injective or constant, the first question you should ask is, well, can both cases actually arise? Can you give me a situation where the limit will not be constant? Good. So we could do Fn of Z is Z plus 1 over n. Now, will that work? Not if we're mapping D to D. I'm sorry? We have some range issues. How can we fix the range issues? You just blow things up. You put range issues. So let's do Fn of Z is maybe Z plus 1 over n over 100,000. I think this is probably because I was giving candy away last night, and so I have 100,000 candy bar on my mind. I will have a candy day here at some point in the near future because one, I think college students like candy, and two, we have way too much candy at home. So will this function be injective? Yes. Will this map the disk to the disk? Yeah, bringing the 100,000 is going to make it very safe. So always just throw in large numbers. The year is also a good number to just throw in. And then the limit is going to be just the function Z, so not constant limit. So limit as n goes to infinity of Fn of Z is just Z over 100,000. So this quick analysis is enough to show us that both cases actually arise. Okay, the proof, I'm going to just sketch. Assume the limit is not constant. So we can find Z1 and Z2 such that F of Z1 does not equal F of Z2. And so we have 2 points that are well separated. And we can let, let's say, Gn of z be Fn of z minus Fn of z1. And then G of z will be F of z minus F of z1. So where is G of z equal to 0? Z1? Z1 and Z2. Because we're assuming, I said assume it's not constant. Right, okay, so we have two places where, okay, why Z2? So I think I wrote this wrong up here. What I want to do is we're assuming it's not constant, but assume there exists Z1, Z2 such that F of Z1 equals F of Z2. Because if there's no such Z1 and Z2, what do we know? If you can't find 2 points where the function is different, what must be true about the function? Not constant. Well, we're assuming it's not constant. And if the function is not constant and there aren't 2 points where F of Z1 does not equal F of Z2, what must be true about the function? It's then injective. And so we're trying to prove by contradiction that it's injective. So if we assume that there are 2 points that are sent to the same thing, you will basically say, assume the function is non-injective. And we're going to get a contradiction from that. So assume not injective, not constant. Okay. So we know that F of Z minus F of Z1 is 0 at Z1 and Z2. What about Gn of Z? When is that equal to 0? At Z1. Any other points? No. Because Fn is 1 to 1. And this is by assumption. So we're assuming that our function is non-injective, so we can find a Z1, Z2 such that this is true. Because each Fn is injective, the only 0 of Gn is going to be Z1. So if I draw a sufficiently small ball, circle around Z2, let's call that gamma. What do I know about the integral over gamma? I'll put in the 1 over 2 pi I of Gn of Z prime over Gn of Z dz. What would that equal? 0. Why? Holomorphic has no zeros, yes. Yes. So this basically counts the number of zeros and the number of poles inside. And because there are no zeros of Gn, Gn of Z is fine. Has no poles, everything's holomorphic. So this equals 0. What would the integral of 1 over 2 pi I, integral over gamma of G of Z prime over G of Z dz equal? Okay, why 1? So how do we know there's only 1 0? But how do we know there's only 1 0? Good, by itself, we know the function's not constant. So if I could choose for any gamma, if I could always find another zero, what would happen? Assurance of accumulation. This is by accumulation. No other zeros if gamma has a small radius. No. If you imagine that there are some other places, they can't get too close. Because if I could always find for any radius a point where g of z equals 0, then g would have to have a sequence of accumulation. G would be constant, and we're assuming it's not constant. Okay, what must be true about these two integrals? So the hope is that these are the same as n goes to infinity. And the reason is we are integrating over a compact set or curve of a fixed size. We have nice continuous functions. Everything is well behaved. So the limit of the integral is the integral of the limit. And that's the proof. Okay. So this proves that if we have a sequence of injective functions, holomorphic, converging uniformly in compact sets, then we're either injective or constant. What question do you think I should ask about this now? Related to the other questions we've been asking all year. Yes. Yeah, what about the real case? Do you think that we will still have convergence if we have a sequence like this? So say we have sequence fn of x, say it's real analytic. That'll be my analog of holomorphic, because holomorphic means analytic. Injective. What is it? Bounded, converges uniformly on compact sets. Must the limit of Fn be either constant or injective? What are your thoughts? Without even thinking, what are your thoughts? No! Why not? What does real analysis lack? Yeah, we don't have integrals like this in real analysis. So all of these consequences of contour integration are completely absent. So the question is, can we try to come up with a counterexample in real analysis? And I debated either making this an extra credit problem or an exam question. I decided instead I'd rather actually spend some time on the thought process. And so I was thinking about this as I was walking to the department today as to what functions to try. And my first thought, was a stupid thought, was try, say, maybe 1 minus t, be 1 over n z plus 1 minus 1 over n z squared. Why would that be an interesting thing to try for Fn? Yeah, goes from z to z squared. So maybe, but a quick inspection tells me there's no way in hell this can possibly work. Why can't this possibly work? Why don't I even have to do the calculation? I'm sorry? Well, that's the whole point, is I'm trying to have it converge to something that's not injective. Is that maybe, it starts off at z, which is injective, and then it converges to z squared, which is not injective. Okay, but I mean, maybe I restrict my interval. But there's got to be a reason why there's a really obvious reason why this doesn't work. Any Star Trek fans here? Oh dear, okay. So we'll see if this works. So Professor Stark and I are going to be teaching a winter study on the science of Star Trek. And in one of the more unbelievable episodes, they have this super wonder whiz kid, who you might know from Big Bang, Will Wheaton, who plays Wesley Crusher, is trying to get into Starfleet Academy. And he's not quite good enough, even though he's been serving on the Enterprise for years and saved it numerous times, he's actually not good enough. So you think you have trouble getting into grad schools and stuff like this. Anyway, he's taking a test, and they need to calculate what is the correct ratio of matter-antimatter for the interaction, given that you are a ship traveling like warp 7 in a Cochrane field of the following, blah, 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 blah. And so people start doing the calculation. What do you think the correct ratio of matter to antimatter is? For this controlled reaction, what would you guess? 1 to 1, right? It's a trick question. It's always 1 to 1. So all the other stuff that they're putting in doesn't matter. Look at this function. Oops, I slipped. I even wrote z, right? I shouldn't be writing z. I should be writing 1 over n x plus 1 minus 1 over n x squared equals fn of x. Now, can you tell me why this clearly can't work? Yeah, if it works for the real, it would work for the complex. If works for real, works for complex. And this is why I really wanted to spend the time talking about examples like this. There's no way I should be searching through something like this. Because if I try anything like this, it clearly can't work because my function is holomorphic. So it's not going to work. So when you're trying to find your counterexample, this guides you on where you can be looking. I have to look at a function that's real analytic, but not complex differentiable. Any thoughts? So I need a function real analytic, but not complex differentiable. Any thoughts? So we could try 1 over x, but that's going to have the same problems for real as complex. So I need, yes. So log potentially, because I can't define log on the whole range, but depending on what my region is, I might be able to define log on the region. So I'm not going to say log can't be done. I'm just going to say that's not the one I want to look at. I need a function that is real analytic, has some nasty properties, and is not complex differentiable. So this is a function you need to know on your list of your top 10 functions. This has to be one of your go-to. When you do probability, you need to know the Cauchy distribution. You can have debates as to whether or not it has mean 0. I'm fine either way, even though it's not integral. I can see it fine. It clearly has infinite variance. So here is the function you should really know. G of x equals 0 if x equals 0. Anybody remember the function now? All of its derivatives are 0 at the origin. E to the negative 1 over x squared. You need to know this function. It's a great example. Yeah, in some sense, functions like this are absolutely terrible because every derivative is 0. This is basically L'Hopital. It is, well, although then the question is, of course, depending on what we mean. So if we are insisting on real analytic, we can't use. So cannot use if real analytic, can use if just say differentiable. And if you look at the statement of the theorem, it says we have a sequence of injective holomorphic functions. Well, holomorphic just means what? Holomorphic technically means differentiable. And then as a theorem, you get that it's real analytic. So you can argue as to whether or not we can use something like this. All right. So what I want to do now, anybody have any thoughts about what might be a good way to try to use this function? Any thought? Yes. Okay, so how would you do it? So we have our function g of x, and the function, if I plot it, it's going to look something like this, essentially 0 for all practical purposes. This is a function that is not going to be one-to-one. So I want to have something that in the limit converges to g of x, right? So I want my functions, gn of x equals blah plus blah, and as n goes to infinity, I want it to maybe converge to something like g of x. First thing I tried, okay, so I tried, so yeah, except unfortunately I used the letter f, so let f be, if x is not 0, it's either the negative 1 over x squared, if x equals 0, it's 0. Why do you think I defined it like this? Mathematica is not happy with the definition of either the negative 1 over x squared when x equals 0. So I'm defining it like this so that the computer will allow me to work with it. So my function g is just x over n plus f of x. As n goes to infinity, what does x over n go to? Goes to 0, right? And so this will converge to f of x. And then I calculated the derivative. If x is not equal to 0, the derivative is very easy to compute. If x equals 0, you just use L'Hopital's rule, it's not so bad. And I wrote down what it is. And so now what I'm plotting here, the blue is my function g of xn. And this is taking n to be, I think, 0.05. And then the, what do you call that, gold? The gold color is the plot of the derivative. What can you tell me about the function g just by looking at the plot of the derivative? I'm sorry? What's approximately constant? No. Right. So if I tell you that my speed is approximately flat at 20, does that mean my function is constant? So think of the blue as your distance and the orange as your speed. So if your speed is constant, is your distance going to be constant? If your speed is, say, 20 meters per second, you'd expect as more time elapses, you've gone further from home. It's only if your speed is 0. But so what can you tell me about the function g if I tell you that its derivative is approximately around 20 for all these values? What special, yes?
The value for the 20x is barely increasing.
Okay, it's about, good, it's increasing. Why must it be increasing? Derivative is positive. And so if you have a function that's increasing, what must be true about it in terms, it must be what? Injective, right? This is a really nice way to prove injectivity. If the derivative is positive, it must be injective. So now what I do is I play the game. We're going to watch a little movie, and we're going to let n increase very slowly. And you can see that as n increases, eventually the derivative becomes negative. And when the derivative dips below 0, clearly the function is no longer going to be injective, because now it decreases for a while, then it starts increasing again and goes over. So now what we can do is we can rewind time. And so we can see, at around 1.09, the derivative is still positive. And I could zoom in a little bit. And then it looks like there's going to be that point where it first touches. Is it still injective here? Yes, it's still injective. It's like the function x cubed. If you look at the function x cubed, the first derivative is positive everywhere, except at the origin. And at the origin, the derivative of x cubed is 0. So you go positive, 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 0, positive, positive, positive. Your function is one to one. Your function is still increasing. If I go a little bit beyond this key critical point, is my function injective? No. Doesn't matter. It technically just says I have a sequence of functions. And so I could have them indexed by parameter. If I wanted to choose things to be integers, I could play special games with rationals and take rational approximations. So if I wanted to worry about that, let me just take a snapshot of this. Back over here. So we have a problem with this. So the difficulty is I can get it so that it's not injective, but the problem is that when I have that critical threshold, it's still injective at that critical threshold, and then it's only past that point that it's not injective. And so we want a sequence of functions that is injective for all values of n, and then it's the limit that's not injective. And so here, unfortunately, it's still injective at the key value of n. So I need to go back to the drawing board and tweak it a little bit. And so here's the next tweak I looked at. And so a of x is the function very similar to what we had before, very similar to e to the negative 1 over x squared. This is a really powerful tool in analysis. It's a really nice trick. You introduce a small little extra parameter. For those of you who have read Weinitz Sinak, they actually have something like this where they introduce an epsilon in one of these low-lying zero calculations. I know there's a couple of people who are taking auditing this class who have done that, where every finite moment you're okay, but in the limit, you have some new behavior. So for any finite value of a, e to the negative 1 over a squared plus x squared is fine. Actually, I should probably change the definition. It really probably shouldn't be 0 at 0. What should it be? When x equals 0, it should just be should really be negative 1 over a squared. Should I really fix this? Yeah, why does it really matter? In terms of plotting, if I have 1 point wrong, does it really matter? I can put negative 1 over a squared, and as long as a is not 0, it's fine. Yep, right? Okay, I'm just trying to see why is the a now in red and what comes below. Do you see Am I doing something wrong in Mathematica? All right. So over here, if x equals 0, it should still be okay, correct? So the simplest way to fix this, if x does not equal something huge that's completely outside of my range, then it's still going to just display this everywhere. So now let me look at what's going on. If I'm in a sufficiently small neighborhood about x equals 0, as long as a is not 0, ax is going to be much, much larger than f of x, a, right? And so is it going to be injective when a is large? Well, let's see. What happens as a gets large? Well, the larger a gets, the bigger the denominator we have in the exponential of -1 over a squared plus x squared. So then it doesn't even matter anymore. It's going to change the decay a little bit, but how large can the exponential of that negative thing be? At most 1. So I've got ax. So I would expect for a lot of values of x and a that the ax should drown out the f of xa term. So does that seem reasonable that there's going to be a regime of a and x where the xa is going to beat the f of xa? Now, what happens as a gets smaller and smaller and smaller? Well, as a gets smaller and smaller and smaller, again, if I get really, really close, then x squared is so small, the denominator is essentially a squared. But what happens to ax as a goes to 0? What's that going to go to? It's going to go to 0. And so if I look at my plot here, I'm plotting the values where a goes from 1 all the way down to 0.0001. And you can see as we go smaller and smaller and smaller, does it still look injective? Yeah, the derivative is still going to be positive. What will happen in the limit as a goes to 0? What function will we get? We can ask Mathematica to calculate it. Mathematica doesn't like it. It's now doubled things. It's got something in red. So it's telling you, I really, really don't like you asking me to do this. But if you look at what's going on, the blue is essentially what we saw before. For our plot, we see things like 10 to the -73, which is essentially telling us, boy, it's small, in neighborhoods like this. So we really, really should not be plotting it like that. Sorry, let's paste this and I'll put back a good plot. And so the point is, I think here is a function that works. It's a differentiable function. It's injective. But the limit is not going to be injective. Basically, we can take a to be 1 over n. As n goes to infinity, we have a goes to 0, and then our function BA of x converges to the e to the -1 over x squared 0 function. And this shows us that the real case can be extremely different. So this idea of sequence of injective functions has to converge to an injective function. It's not true in the case of just real differential. And again, I really wanted to spend time talking about something like this because a big part of this is trying to get a sense of how do you attack a problem like this? How do you start the process? And as I was walking, to the department today, my first thought was to start with functions like z and z squared. Z is injective, z squared is not. Is that a reasonable thing to try? Yes, I mean, you could say as well, Professor Haman, why would you even do that? You've got to know that that can't work for the following. And yes, I should have realized more quickly that there's no chance of finding a counterexample like that. And as soon as you realize that, that then helps you with your search. Okay, I'm not going to find an example if I just stick to functions that have analogs that are complex differentiable. So what I have to do is I have to look at some real functions that are just crazy. And e to the negative 1 over x squared, if you try complexifying that, e to the negative 1 over z squared, if you approach along the imaginary axis, it goes to plus infinity. So this at least gives me a candidate to search for. And then I can try to play an interpolation game. Okay, any questions about this example? So again, yes. So f is what we're calling our function e to the negative 1 over x squared. And so on this page, I was just modifying it slightly to give me this extra parameter a. And the reason is e to the negative 1 over a squared plus x squared is always defined for every value of x. I have just one definition that's needed. Whereas if a equals 0, I now have to define it slightly differently if x equals 0. All right. So the proof of the Riemann mapping theorem then comes down into 3 steps. So step 1 is we use the logarithm to say a different kind of log. Without loss of generality, we can map from the disk to the disk. We might as well assume that our initial region is the unit disk. The second one is the subset of the unit disk. Then we use the Mantel to get a map with maximal derivative at the origin. And then finally, we show it's conformal. If it's not conformal, it's going to contradict maximality. So this is how a lot of proofs work. You show that there exists something with a desired property. You find a good representative, the best representative, the representative that has the largest possible value. And then you show that if everything doesn't work out the way you want, you could have found something better. And since you already found the best, you can't do anything better. Now we're going to try to get the maximal derivative at the origin. What do you think the maximal derivative at the origin will be? We have a function that maps a subset of the unit disk. So omega is a subset of the disk. F maps omega to D. And I'll call it F star. This is our special maximal. What do you think would be true about the value of its derivative at the origin? 1. Could it be larger than 1? Why not? So we have Schwarz's lemma. So probably there's a reason why we proved Schwarz's lemma before proving the Riemann mapping. Another thing you could do is you could look at iterates. You could look at maybe F star of Z. Are we allowed to compose F with itself? It depends where things are defined, right? We have F maps omega to the disk. We could have it mapping to some points that were not originally in omega, and then it wouldn't be clear how to apply F star there. But if we could do this, then by the chain rule, we would actually get the derivative. If the derivative started off being greater than 1, when you compose it like this, it would be magnified. It would be even larger. But we don't necessarily know that we can apply F star to F star. Okay, so we have 3 steps. So the first step is use the logarithm. So we have omega is open, simply connected, and it's not all of C. So because it's not all of C without loss of generality, what does that mean? If you're not all of C, what do I know? There's an element that's not in omega. So the book uses elements. What else could you use for that element? Without loss of generality omits 0, right? So, without loss of generality, 0 is not in omega. And so because it's simply connected, here's 0, there must be some way to have a branch cut and define logarithm. Oops. And so here's my set omega. I can define the log on omega. And then what the book goes through and does is a sequence of calculations. It shows, let's say you have z in omega, and you'll have f of z. So you have w in omega, you have f of w. And then the claim is f of z does not equal f of w plus 2 pi I. And the reason for this is, let's say we have f of z is the log of z. E to the f of z is e to the log of z. And from our properties, what does that equal? It's going to just equal z. What would happen if we had 2 points whose image differed by 2 pi r? What would have to be true if the image differed by 2 pi r? When you exponentiate, if we have e to the f of z, and we have e to the f of z plus 2 pi I, what do we know about these two values? They're the same. But e to the f of z is just z, right? And over here, if this was e to the, say, f of w, you would get w. And what would this violate? So it violates 1-to-1. So what you can basically do is you can go through and you can say that if I take on the value f of z, there's no other input such that the f of w is basically 2 pi I plus f of z. And what the book then goes through and says is, well, look, here is some point f of w plus 2 pi I, which we don't obtain. No value of c, no value of z maps to this. In particular, we can draw a small little ball about this, and nothing is mapped in here. If not, you would have a sequence of points zn converging to some, say, z star. And if you had a sequence of such points, so no matter how small the radius were, you were coming in like this, it would violate injectivity. So you just go through and you see that you can't have something like that. So that you have to omit not just f of w plus 2 pi I, but a small little ball about that. Okay, so now we know we have a situation where here's omega, here's some point f of w plus 2 pi I, and here is a little ball that we avoid. And so we can then look at this new function, g of z is 1 over f of z minus f of w plus 2 pi I. Do I ever have to worry about this being 0? No. And you can show that this is now going to give you a bounded map. Is it's going to map us into a small region. Other things you could do, if you wanted, is if I have, without loss of generality, let's assume it's the point 0 that we omit. And then, here's my omega over here. I could just take the function f of z is 1 over z, and then that would map omega to something inside the unit disk. So the whole point of step 1 is that there are ways to pass from mapping omega to the unit disk to say, I might as well assume that omega just starts off inside the unit disk. I don't want to, I don't want to rush through, step 2 and step 3. So we will probably talk about those next time. All right. Have a good rest of the day.